All right, I'll just give you a brief overview of the last thing that we covered in chapter 6. We looked into heat engines. Heat engines primarily due to the fact that heat engines are the devices that convert heat into work. We looked into the fact that work can be converted into heat directly and completely. But for the heat engines, we looked into the fact that if heat is to be converted into work, heat engines are the devices that are used, and there are four characteristics of heat engines that must be met in order for a heat engine to operate. The first characteristic was that the heat engines, they receive heat from a high temperature source. This could be solar energy, oil furnace, nuclear reactor, or some other source. So they receive heat. Since heat has to be converted into work, so heat from high temperature source is necessary. And the second characteristic is that they convert only part of this heat to work, and that work is usually in the form of rotating shaft. It is not necessary, but usually. Third characteristic is that the remaining portion of the heat, one portion is converted to work, the remaining portion of the heat, it is rejected as waste to a low temperature sink. The sink could be atmosphere, rivers, or other. All right. And the fourth characteristic is that the heat engines, they operate on cycle. All right. So these are the four characteristics. Now, once you're familiar with these four characteristics, we'll look into the most common type of heat engine, or the heat engine that ideally fits the definition of a heat engine. The work producing device, heat engines are work producing devices that best fits into the definition of a heat engine is the steam power plant, which is an external combustion engine. Now, IC engine or the gasoline engine, automotive engines, they are internal combustion engines. That means the combustion is taking place within the chamber or within the piston cylinder assembly. However, steam power plants, they are external combustion engine. That means combustion or heat generation is taking place outside the system. I'll show you how. This is a steam power plant. You have four components to this, the basic, very basic schematic. The boiler, four components: turbine, condenser, and pump. How is it working? You essentially have over here, right before the entrance of the boiler, you have liquid at high pressure, high here, which is about to enter into the boiler. As this high pressure liquid is about to enter into the boiler, the purpose of the boiler is to convert to provide this liquid with the heat or energy input. So you have an energy source such as furnace, which is outside this system, and it is providing heat to the boiler, or in other words, it is providing heat to this high pressure liquid. As high pressure liquid comes out of the boiler, it is in the form of high pressure, high temperature steam. So this Q in is basically the heat that is being provided from a high temperature source. This high temperature source provides you heat, which is being transferred to the fluid, and fluid in this case is water. As a result of the heat being transferred, the liquid phase of the fluid at high pressure converts into steam. Now, as this steam is about to enter into the turbine, what happens is the high pressure, high temperature steam has high enthalpy. And as the steam leaves the turbine, it leaves as low pressure, low temperature steam. The energy which is being consumed, the energy that is being extracted from high pressure, high temperature steam by converting it to low pressure, low temperature steam is being used in rotating the turbine, which is attached to the shaft. Thus, a work out is being generated. So the heat that was being provided to the boiler, it is being used in rotating the turbine, or it is being used in creating work output. Now, in order to complete the cycle, this is low pressure, low temperature steam. You have to enter or apply this low pressure steam into low temperature steam rejects it to a low temperature sink in the form of Q out and converts into low pressure, low temperature water. This water, in order to complete the cycle, it is being passed through the pump where pump is being provided with work in, and as a result of this work in, this water again gets to the or this liquid gets to a higher pressure, which is the pressure of the boiler. So this fluid is basically completing a cycle. Four characteristics of heat engine. Number one, high temperature heat source giving in heat. So there is Q in. Number two, some of this heat is used in producing work, usually in the form of rotating shaft. That work is work out. Remaining portion of the heat of Q in is rejected out to a low temperature sink. It is rejected in the form of Q out, and it the heat engine is operating in a cycle. Cycle is basically that of a fluid. Fluid is moving in the form of cycle. It started from one state, moved into several states, and came back to the same state at the end of the cycle. Is this heat engine, the working of steam power plant, clear to you?
Yes, sir.
All right.
Yes, sir.
So the heat engine, what is it is doing is producing work out. This is work out of a heat engine, and a portion of this work out which is being produced is utilized in running the pump. That is work in. The remaining portion of it is basically the net work out of the heat engine. So the net work out of heat engine is essentially work in or work out minus work in. This is the net work out of the heat engine. Similarly, the Q net into the system, heat coming into the system, Q net into the system is essentially Q in coming into the system minus Q out that is being rejected to the system. This is the net heat into the system. Now, if you let me remove everything from slide. This gray region, basically marks the boundary of a steam power plant. Is there any mass which is entering into this power plant or which is leaving this power plant?
No, sir.
No, sir.
So there is no mass which is entering or leaving the system. So if we consider this gray region as a system boundary, is it a closed system or an open system?
Closed system.
All right, so this system is a closed system. And for closed system, the energy balance equation is Q minus W equals to delta U, where Q is Q net into the system, W is work net out of the system. It is essentially equal to delta U. And what is happening or how does the equation change if a closed system is undergoing a cycle?
Sir, work done will be equal to 0.
Delta U.
So sorry, delta U will be.
This is dependent upon state. Delta U would be equal to 0. You would essentially have, for a closed system, delta U is 0, which is undergoing a cycle. And you will have work net out is equals to Q in minus Q out. That means total heat provided to the system minus the heat rejected out of the system would give you the net work produced by the heat engine. Clear enough?
Yes.
Yes, sir.
Now, how do you define the thermal efficiency of your system? In the equation, Q out represents the magnitude of energy wasted in order to complete the cycle. If you will not complete the cycle, if the low pressure, low temperature steam is not passed through the condenser, you will not be able to get the liquid phase water at high pressure, high temperature. So you'll not be able to complete the cycle if this heat is not rejected to the sink. That means if Q out cannot be, if Q out, it cannot be equal to 0. The net work output of heat engine is always less than the amount of heat input. You wanted heat to be converted into work, but in order to convert heat into work, you'll always have Q out. That means not all of the heat could be converted into work in a cyclic engine. All right. So only the part of heat transfer to the heat engine is converted to work. How do you define the efficiency? It is the fraction of heat input. This is what you are providing to the system, which is converted into net work output. This is the measure of the performance of a heat engine, and it is called thermal efficiency, normally represented by NTH. So work net out is what you're getting out of it. Work net out is Q in minus Q out. What is being provided to the system? Heat is provided to the system. So the fraction of heat input that is being converted into useful work is Q in minus Q out. And you can always write it as, you can divide all the values by Q in. So Q in divided by Q in would essentially be 1. Q out divided by Q in would remain as it is. So 1 minus Q out over Q in is the thermal efficiency. If you have a source which is at high temperature and it is providing heats to two heat engines, one is engine 1, the other is engine 2, the same amount of heat input. Engine 1 converts 20 kilojoules as the output, and engine 2 converts 30 kilojoules as the network output. So engine 1 is essentially rejecting 80 kilojoules of the heat provided, whereas engine 2 is rejecting 30 kilojoules. Efficiency would be net work output for 1 divided by the heat input, which is 20%, and for the engine 2 it would be the net work output 30 divided by 100, which equals to 30%. So this is how you find out the efficiencies of the heat engine, thermal efficiency of the heat engine. Clear enough?
Yes, sir.
Yes, sir.
All right. Now, moving on, whether you're talking about cyclic devices such as heat engines or you're talking about refrigerators and heat pumps, we'll be looking into refrigerators and heat pumps in few minutes time. They often operate between high temperature reservoir, which is known as TH, from which the heat input is coming, and a low temperature reservoir which is acting as a sink at a low temperature, which is represented by T, having a subscript of L. T. Now, instead of writing Q in or Q out in the form of cyclic devices, you represent heat coming from the high temperature source as Q subscript H, high temperature source, and for the heat coming in from or going in from coming in or going to the low temperature sink is basically represented as Q subscript L, which is representing the heat associated with the low temperature reservoir. So the network now could be expressed as, if you remember, work net out was represented by Q in minus Q out, which is essentially QH minus QL. So you replace in and out with the reservoirs. This is representing high temperature and this is representing low temperature. And the efficiency of the device then could be expressed as 1 minus QL over QH, which was initially 1 minus Q out over Q in. So the high temperature reservoir is giving in the heat at the rate of QH. Net work out is the same. The low temperature reservoir sink is extracting the heat at the rate of QL. So you will associate it with the reservoir. Clear enough?
Yes, sir.
Yes.
Good. So now we'll have an example. All right, before that, information, the efficiencies of various known engines. The gasoline engine or the petrol engine has an efficiency of 25%, the diesel engine having an efficiency of 40%, and power plants could have efficiencies, thermal efficiencies as high as 60%. That means 60% of the heat provided to a power plant, which is a gas steam power plant, would essentially convert into work. The rest of it would be rejected to the low temperature reservoir as heat out. The question comes, can we save Q out? Is there a possibility of saving Q out? That means in a steam power plant, the condenser is the device where large quantities of waste heat is rejected to the rivers, lakes, or atmosphere. So is it possible that you complete the cycle? Can we not just take condenser out of that plant and still and save all the waste energy? The answer is essentially no. The simple reason is that without a heat rejection process in a condenser, the cycle cannot be completed. And if the cycle cannot be completed, the heat engine cannot essentially operate because it operates on a cycle. To illustrate this example, let us have a piston cylinder assembly. Within the piston cylinder assembly, you have a gas which is initially at 30 degrees centigrade, and there are two stops that are being placed within the piston. This is the lower stop, and these are the upper stops. The piston head contains certain amount of load on top of it. Now, if the piston head is brought in contact with the reservoir, which is at 100 degrees centigrade, due to the temperature difference, there would be heat which would be transferred to the gas. Heat transferred to the gas, or heat energy in form of heat transferred to the gas, is 100 kilojoules. As a result of that heat transferred, there are two things that would happen. Number one, the temperature of the gas would go up. Internal energy would go up. Number two, the pressure would cause the piston to move, and the piston would move from its initial position upwards until it reaches to the upper stops. And in doing so, heat has been consumed. Now, my question is, if I take off the load is being removed. And now I want my system to come back to the initial stage. 15 kilojoules has been consumed in moving the piston and load upwards. The remaining 85 kilojoules are still within the piston cylinder assembly. I have produced the work that the remaining amount of energy I want it to be transferred back to the reservoir so that my system comes back to the initial condition. But if I bring my system, this reservoir, which is at 100 degrees centigrade, this 100 degrees centigrade reservoir in contact with this position of the second state of my system, would there be any heat transfer from the piston, from the cylinder to the heat reservoir?
No, sir.
No. So essentially, I cannot come back to my initial condition unless and until I reject this 85 kilojoules of energy to a reservoir which is at a lower temperature as compared to the source reservoir. So heat out has to be 85 kilojoules. This is the extra heat within the system. It has to be rejected in order to bring the system back to its original position. And in order to do that, you have to extract the amount of heat by bringing it in contact with the reservoir, which is at a lower temperature, so that the heat transfer could take place. So you need to have the heat rejection process in order to complete the cycle, in order to bring the system back to its original position. In other words, a heat engine cycle cannot be completed without rejecting some heat to a low temperature sink. All right, and that means that every heat engine must waste some energy by transferring it to a low temperature reservoir in order to complete the cycle, even under the idealized condition. All right. So
Right, sir.
saving Q out is essentially not possible. Now let us have a look at this example. It says that heat is transferred to a heat engine from a furnace at a rate of 80 megawatt. If the rate of waste heat rejection to a nearby river is 50 megawatt, determine two things: the net power output of the heat engine and the thermal efficiency for this heat engine. This is the schematic. You have a furnace that is giving you heat, to the heat engine at the rate of 80 megawatts. The heat is rejected from the heat engine to the river or the low temperature sinks at 50 megawatt. You have to determine the work net out, and you have to determine the thermal efficiency of the heat engine. So if you could uh, use 2 minutes time and find out for yourself net power output and thermal efficiency. First find it out and then I'll explain how to do it. I have 2 minutes, find it out, and then I'll explain the solution.
Okay, sir.
Okay. All right. What's your good name?
Ashad Ali, sir.
Sorry?
Ashad Ali, sir.
Ashad Ali. Ashad, so could you explain me what is your answer for the net power output?
Sir, 30 megawatts.
Very good. So the net power output, W net output, I'll place a dot on top of it since you're talking about the rate, is essentially QH dot minus QL dot, which is essentially 80 minus 30, sorry, minus 50, which comes out to be 30 megawatt. Simple enough. The thermal efficiency, NTH, it is also defined by 1 is Q dot L over Q dot H, or you could also find it out work dot net out over Q dot H. Work dot net out is essentially 30 megawatt, and the essentially Q dot H is 80 megawatt. So you will have 3 over 8. Uh, what is the answer for this? 3 over 8? 0.2 something?
0.375.
0.375.
0 point?
375.
375.
Yeah. 0.375 or 37.5%. This is the efficiency of this heat engine. So if you look at the solution, again, the net power output Q dot H minus Q dot L is 30 megawatt, and the efficiency is work net out divided by Q dot H. This comes out to be 37.5%. Simple enough. Moving on, we'll be looking into the Kelvin-Planck statement, which is basically the statement for heat engine, second law statement for heat engine. It says, we know that no heat engine can convert all heat it receives to useful work. So this is the limitation on thermal efficiency of heat engines and forms the basis of Kelvin-Planck statement for the second law of thermodynamics. The statement says that it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce net amount of work. So why why do you think that the statement is correct, or what is the problem? Why is it impossible?
सर क्योंकि जब तक हम हीट रिजेक्ट नहीं करेंगे सर हमारा साइक्लिक प्रोसेस कंप्लीट नहीं होगा.
वो तो ठीक हो गया, लेकिन स्टेटमेंट में क्या चीज ऐसी है जो इसको निगेट कर रही है?
Sir, low
What is
rate
it?
reservoir होना चाहिए.
Sorry?
सर फर्स्ट स्टेटमेंट सर
जी?
जिस तरह एफिशिएंसी 100% नहीं हो सकती, जिस तरह एफिशिएंसी 100% नहीं हो सकते फर्स्ट स्टेटमेंट में, तो उसी तरह ये भी नहीं.
Hey, what's the problem in the statement? If you look at this statement, what is the issue? It's impossible for any device. Why is it impossible for any device to operate on a cycle to receive heat from a single reservoir and produce net amount of work? What is it that is missing in the statement? Or that negates the second law, or that
Heat out.
places a restriction?
Single reservoirs.
Very. You need to have two reservoirs, the high temperature and the low temperature. So if you have a thermal energy reservoir that is giving you energy at Q dot H 100 kilowatt, and the same would be converted into 100 kilowatt work. If you don't have QL, QL has to be rejected to a reservoir. If the reservoir is not there, that means QH is coming and it is creating 100 kilowatt of work, which is not possible. So a heat engine must exchange, it must exchange heat with a low temperature sink as well as a high temperature source to keep operating. Another view of looking at the Kelvin-Planck statement is that the Kelvin-Planck statement can be expressed as no heat engine can have a thermal efficiency of 100%, or as for a power plant, the working fluid must exchange heat with the environment as well as the furnace. So we have looked into one component, which is engine. Let us look at
सर आपकी आवाज डिस्टॉर्ट हो रही है.
another type of devices. Is it clear now? या अभी भी distort हो रही है? अभी आ रही? Is the voice clear or not?
सर अब सही है.
All right. So heat, the transfer of low temperature. That means it flows in the direction of decreasing temperatures naturally. This heat transfer process occurs naturally and it doesn't require any device. However, if you want to do the opposite, the reverse process, it cannot occur by itself. There has to be a device that transfers the heat from low temperature medium to high temperature medium, and these special devices, they are called refrigerators. Now, the refrigerators, like heat engines, they are cyclic devices, and the working fluid in the refrigeration cycle is a refrigerant. One of the refrigerant you might have used in some of the numericals, R134A. It is used in the refrigeration cycle. The most frequently used refrigeration cycle is the vapor compression refrigeration cycle. We'll have a look at this refrigeration cycle as it is. So let's say I have this refrigerated space with me and I have brought some vegetables which are currently at room temperature, and I want to keep them cooled, let's say at 10 degrees centigrade. I'll place them in the refrigerated space. Here you have R134A refrigerant which is flowing in the pipes, and at this condition before entering the evaporator it has a pressure of 120 kilopascal and minus 25 degrees centigrade. As the refrigerant enters into the evaporator, heat from the vegetables would be transferred to the R134A refrigerator, and as it exits the evaporator, it has gained heat and it has temperature minus 20 degrees centigrade. The temperature has increased. So the refrigerant has extracted the heat out of the vegetables or from the refrigerated space, from the refrigerated from the lower compartment of your fridge, or for that matter for an upper compartment of your fridge, whatever it is, heat has been extracted. That's why the temperature in the refrigerated space is low. Now this refrigerant, it is then compressed. Since it is containing heat, it is being then compressed to a higher temperature and higher pressure. Using a compressor, you make the refrigerant attain higher temperature and higher pressure. Let's say the outside temperature is 25 degrees centigrade. So that the refrigerant, when it enters into the condenser, the temperature of refrigerant is 60 degrees centigrade. Outside there is 25 degrees centigrade. So the refrigerant throws its heat away out into the kitchen or the area which is surrounding the refrigerator. So to your atmosphere, the refrigerator is throwing out the heat. It is rejecting the heat. Then, in order as it exits the condenser, the temperature of the refrigerant has decreased to 30 degrees centigrade. But in order to enter into the evaporator, it still has to come down to minus 25 degrees centigrade so that it could extract the heat out of the refrigerated space. In order to do that, the refrigerant is passed through the expansion valve or throttling valve, which results in a decrease in pressure and substantial decrease in temperature. If you remember, during the throttling process that we have studied, pressure decreases significantly and so does the temperature. And in such a case, the pressure and temperature both comes back to the original condition of 120 kilopascal and minus 25 degrees centigrade. That's how the cycle gets completed. So this is again, if I remove all the ink and if I show you this gray region, this is your engine or your refrigerator. This is the device. All these components make up the device. Essentially, what is happening? Essentially, your refrigerator is at 10 degrees centigrade. Your kitchen is at, let's say, 25 degrees centigrade. What actually is happening? This device, which is known as a refrigerator, this device is essentially taking the heat from low temperature and essentially transferring the heat to a high temperature source. So it is taking the heat from a low temperature sink or low temperature reservoir and it is throwing the heat to a high temperature reservoir, which is a process which does not occur naturally and it requires the special devices. These are called refrigerators. Is the working clear to you?
Yes, sir.
All right. So for refrigerators, you essentially measure the efficiency in terms of coefficient of performance, COP. You don't gauge the effectiveness of refrigeration in thermal efficiency. You gauge the efficiency of a refrigerator in terms of coefficient of performance. And what is coefficient of performance? We'll come to it. In a refrigerator, again, this is the high temperature source or high temperature reservoir. This is the low temperature reservoir. What is required out of a refrigerator? What do you want out of a refrigerator? You want it to cool down the refrigerated space. So your desired output G is coolness or extracting QL out of the refrigerated space, taking out the heat from the refrigerator. This is your desired output. And in order to achieve desired output, you have to do work on the compressor. This is work net input into the compressor. This is required input. If you don't have compressor, the refrigerator would not work. So you define the index of performance as coefficient of performance, which is desired output over required input. So desired output is what? Desired output is QL And required input is what? W net into the system. And W net in is what? Work net in is QH minus QL. You can simply apply the energy balance. If you take this as your device, what is the energy coming into the system? QL plus work net in. They are coming into the system, and Q out or QH is moving out. So work net in is essentially QH minus QL. Clear enough?
Yes, sir.
So you'll essentially have QL over QH minus QL as the coefficient of performance. And if you divide everything by QL, so you would essentially have 1 over QH divided by QL minus 1. This is the coefficient of performance for the refrigerator. So work net is QH minus QL, COPR. R means when you're talking about a refrigerator. Coefficient of performance of a refrigerator is QL over QH minus QL. You divide every variable by QL, so you'll have 1 divided by QH over QL minus 1. Is this clear to you?
Yes, sir.
Now,